Last week, behind closed doors, Huawei revealed something that many people inside the semiconductor industry believed wasn't supposed to happen. Not next year, not 5 years from now, not under the restrictions that have defined the global chip race for the better part of a decade. Because for years, the assumption was simple. The most advanced chips on Earth required access to the world's most advanced manufacturing tools, no exceptions, no shortcuts, no alternative route. If you couldn't access the machines capable of printing the smallest transistors, you would eventually fall behind. The gap would widen, the technology would become harder to copy, and sooner or later, physics would do the rest. That was the theory. Huawei's latest chip may have just challenged it. What's fascinating isn't that Huawei claims to have built a faster processor. Companies make performance claims all the time. What's fascinating is the method. Instead of trying to follow the same path the rest of the industry is taking, Huawei appears to have asked a completely different question. What if the future of computing isn't about making transistors dramatically smaller? What if it's about changing the way chips themselves are designed? And if that sounds like a small distinction, it isn't. Because if Huawei's approach works the way its engineers believe it will, the implications extend far beyond one company, one chip, or even one country. And let's get into it. For more than half a century, the semiconductor industry followed a remarkably predictable formula. If you wanted a faster chip, you made the transistors smaller, then you made them smaller again, and then smaller again. Every generation squeezed more computing power into the same physical space. The process became so reliable that it earned its own name, Moore's Law. Entire industries were built around it. Investors expected it, engineers planned around it, governments structured technology policy around it. Shrinking transistors wasn't just a strategy, it became the strategy. The problem is that physics eventually starts asking difficult questions. The first transistors were enormous by modern standards. Today, billions of transistors fit onto pieces of silicon smaller than your thumbnail. Modern processors contain structures so tiny that explaining their scale almost sounds absurd. Some of the most advanced transistors are now measured in nanometers, dimensions approaching the physical limits of the materials they're built from. At these scales, electrons begin behaving less like predictable particles and more like stubborn reminders that quantum mechanics exists. Signals leak. Heat becomes harder to manage, and manufacturing becomes exponentially more difficult and expensive. The industry has known for years that this moment was coming. The challenge wasn't predicting it. The challenge was figuring out what comes next. Most companies responded by pushing harder in the same direction. Smaller transistors, more advanced lithography, more expensive fabrication facilities, more sophisticated manufacturing techniques. And to be fair, that strategy worked remarkably well. Companies like TSMC, Intel, and Samsung continued extending the roadmap further than many experts thought possible. But Huawei faced a very different situation because Huawei wasn't simply fighting physics, it was fighting access. And the assumption underlying much of the semiconductor world was straightforward. Without access to the most advanced lithography systems, Huawei's ability to produce cutting-edge chips would gradually erode, not overnight, not dramatically, but steadily. And year after year, the technology gap would widen, the leading edge would move further away. That's why what Huawei is proposing matters so much. Because instead of asking how to continue shrinking transistors using tools they couldn't access, Huawei appears to have started asking whether shrinking transistors was the only path to higher performance in the first place. That sounds obvious now, but it's actually a profound shift in thinking. Imagine two cities connected by a highway that's becoming increasingly congested. Most engineers focus on widening the road, adding more lanes, improving traffic flow, building larger intersections. Huawei's approach is closer to asking whether traffic should be traveling on that road at all. Maybe there are tunnels. Maybe there are bridges. Maybe there's an entirely different transportation system nobody has. fully explored yet, and that's essentially what happened with chip design. For decades, most circuits were laid out primarily across a flat surface. Everything existed on a two-dimensional plane. Signals traveled horizontally from one part of the chip to another as processors became more powerful, and those distances became increasingly important, because here's something most people never hear when companies announce new processors. Modern chips aren't just limited by transistor performance. They're limited by communication. A transistor can switch incredibly quickly, but information still needs to move between billions of those transistors. Signals must travel across microscopic highways spread throughout the chip. And as designs become more complex, those pathways start creating bottlenecks. Think about a massive city. Even if every individual car becomes faster, traffic still slows down if people have to travel across enormous distances. The same thing happens inside processors. For years, engineers compensated by making everything smaller. Smaller transistors naturally reduced distances, but eventually another reality emerged. Sometimes the problem wasn't the transistor. Sometimes the problem was the journey between transistors. This is where Huawei's approach becomes genuinely fascinating. Instead of viewing a chip as a flat surface, Huawei began exploring ways to use the vertical dimension much more aggressively, not merely stacking finished chips together. The industry already does that in certain applications. Something deeper, something integrated directly into how the chip itself is designed. And the idea is surprisingly intuitive once you think about it. If two parts of a circuit need to communicate constantly, why place them far apart on a flat plane? Why not position them above and below each other? Why force signals to travel long horizontal distances when they could? Simply move vertically. It's such a simple question that it almost feels obvious, and yet implementing it at semiconductor scale is extraordinarily difficult. The reason is manufacturing precision. When engineers talk about connecting layers of active circuitry, they're discussing structures measured in microns and nanometers. Tiny imperfections can disrupt performance. Tiny misalignments can create reliability problems. Tiny thermal issues can become enormous engineering headaches, and heat is perhaps the biggest challenge of all. Whenever people hear about stacking circuitry vertically, they usually focus on performance benefits, more density, shorter signal paths, greater efficiency. Engineers often focus on something else: heat, because heat is the universal enemy of advanced electronics. Every transistor generates it. Every signal contributes to it. Every layer makes removing it more complicated. If you've ever used a laptop that became hot during intensive work, imagine trying to solve that problem inside a device containing billions of transistors operating simultaneously at microscopic scales. The engineering challenge is enormous, which is one reason many companies approach these ideas cautiously. Huawei, however, had a powerful incentive to move faster. Necessity. History repeatedly shows that constraints can sometimes produce surprisingly creative solutions. Not always. Sometimes constraints simply create limitations, but occasionally they force engineers to question assumptions everyone else accepts, and that's what makes this story interesting. Whether Huawei's exact numbers ultimately hold up under independent scrutiny is almost secondary to the larger idea. The larger idea is that performance gains may no longer come exclusively from shrinking transistors. They may increasingly come from architecture, from layout, from communication efficiency, from reducing signal travel times, from reorganizing the physical structure of computing itself. If you're enjoying this discussion, there's something I genuinely love to hear from you. When you think about innovation, do you believe the biggest breakthroughs usually come from having more resources or from being forced to work around limitations? It's a question that shows up repeatedly throughout technology history, and honestly, I'm not sure there's a single correct answer. Let me know what you think. And because the deeper you look into Huawei's latest chip strategy, the more it starts looking less like a story about sanctions and more like a story about engineering philosophy. One philosophy says progress comes from making the existing path better. The other says progress comes from finding a new path entirely. And the next part of the story is where Huawei begins claiming numbers so ambitious that they could fundamentally change how the industry thinks about chip design itself. The reason Huawei's claims have generated so much attention isn't because the company says it built a faster chip. Every major technology company says that. What has people paying attention is the possibility that Huawei may be attacking a bottleneck the rest of the industry can no longer ignore, because here's the uncomfortable truth hiding underneath the AI boom. The world's most advanced processors are becoming increasingly difficult to improve using traditional methods alone. Every year, the cost of pushing silicon forward rises. Every year, manufacturing becomes more complicated. Every year, the number of companies capable of operating at the leading edge becomes smaller. And at some point, the economics become almost as important as the physics. Think about what it takes to build a modern cutting-edge semiconductor facility. We're no longer talking about factories costing hundreds of millions of dollars. We're talking about facilities costing tens of billions and supply chains stretching across dozens of countries, equipment requiring years to manufacture, components built by highly specialized companies that sometimes have no direct competitors anywhere on Earth. The complexity is staggering. That's why so many analysts believe the future of advanced chips would become increasingly concentrated among a handful of players. The barriers were simply becoming too high, and yet Huawei's approach introduces a different possibility. What if the next major leap isn't primarily determined by who owns the most advanced lithography equipment? What if it's determined by who can architect systems more intelligently? And that doesn't mean lithography suddenly becomes irrelevant, far from it. And advanced manufacturing remains enormously important, but it does suggest the competitive landscape may be wider than many people assumed, because once architecture becomes a larger part of the equation, different strengths begin to matter. Software matters, packaging matters, thermal engineering matters, interconnect design matters, system-level optimization matters, and suddenly the race becomes more complicated than a simple comparison of transistor sizes. This shift is already happening throughout the industry. Look at NVIDIA. The company didn't become the dominant force in AI simply because it produced powerful chips. It succeeded because it built an ecosystem around those chips, software frameworks and development tools, libraries, and infrastructure. The hardware became valuable partly because everything around it became valuable too. Huawei appears to be pursuing a similar principle from a different direction. Rather than competing exclusively on manufacturing technology, it is attempting to compete on system architecture. And that brings us to what may be the most important lesson in this entire story. The semiconductor industry is entering an era where no single breakthrough is likely to dominate everything. For decades, transistor scaling provided a relatively straightforward roadmap. Smaller transistors generally meant better performance. The future looks messier. Progress will likely come from dozens of different directions simultaneously. Better packaging, better cooling, better memory systems, better interconnects, better software optimization, better chip architectures, better power management. Each improvement might appear small individually. Together, they can transform performance. It's a bit like Formula One racing, and the winning car isn't usually faster because of one revolutionary component. It's faster because hundreds of small improvements work together. And that's increasingly what advanced computing looks like. And Huawei's latest work fits squarely into that trend. Now, I want to pause for a second and say something personal. One of the reasons I enjoy covering stories like this isn't because they're about technology alone. It's because they're about how people solve problems. Engineers everywhere face obstacles, and sometimes those obstacles are technical, sometimes they're financial, sometimes they're political, sometimes they're physical limits imposed by nature itself. The interesting part is seeing what happens next. Do people give up, or do they find another route? If you're someone who enjoys these kinds of deep dives into the hidden engineering decisions shaping the future, consider subscribing. Not because subscriptions help an algorithm, but because these conversations are genuinely more interesting when the same group of curious people keeps showing up and sharing ideas. Some of the smartest perspectives I've encountered have come from viewers in the comments section. And speaking of comments, I'd really love your opinion on something. Do you think the future belongs to companies that build the most advanced manufacturing capabilities, or to companies that become the most creative system designers? Because the industry increasingly seems divided between those two visions. What's particularly fascinating is that Huawei's strategy may influence competitors regardless of whether Huawei ultimately wins. That's the thing about technological shifts. Sometimes the impact isn't who finishes first. It's changing how everyone else thinks. If enough companies begin believing that architecture offers bigger gains than transistor scaling alone, investment priorities change, research priorities change, product roadmaps change. The entire industry starts moving in a different direction, and once that process begins, it's difficult to reverse. We've seen this happen before. There was a time when clock speed dominated processor marketing, then power efficiency became critical, then parallel computing became essential, then specialized AI accelerators emerged. Each transition reshaped competitive dynamics. The next transition may revolve around architecture and integration, not because silicon is disappearing, not because lithography no longer matters, but because the easiest gains have already been captured. The future belongs to whoever discovers where the next gains are hiding. And right now, companies around the world are searching for those answers simultaneously. Huawei is one contender, NVIDIA is another, Intel, AMD, TSMC, Samsung, and several others that rarely make headlines but play critical roles behind the scenes. This is still a very open race. That's important to remember. Sometimes discussions about technology become framed as though a single announcement instantly determines the future. Reality is rarely that simple. Building a promising prototype is one thing, and scaling it is another. Manufacturing it reliably is another. Supporting it with software is another. Convincing customers to adopt it is another. The distance between a breakthrough and industry dominance can be surprisingly large. But breakthroughs matter because they expand what's possible. They force competitors to pay attention, and they create new options. And occasionally, they reveal assumptions that everyone else accepted without question. Huawei's latest chip may ultimately be remembered less for its raw performance and more for the question it forces the industry to confront. What if the future of computing isn't primarily about making silicon smaller? And what if it's about using silicon differently? That's a question nobody can fully answer yet, but it's a question worth watching very closely. And honestly, that's why I find this story so compelling. Not because we already know the outcome, because we don't. We're watching the early chapters unfold in real time. A few years from now, we may look back and realize this was a turning point, or we may discover it was simply one interesting experiment among many. Either way, it's worth paying attention. And before we wrap up, I'd genuinely love to hear your perspective. If you've made it this far, drop a comment and tell me what you think the next big breakthrough in computing will be. Smaller transistors, new materials, quantum computing, advanced packaging, something nobody is talking about yet. I read far more comments than people probably realize. And some of the best future video ideas come directly from those conversations. And if you'd like to keep exploring these technology races together, feel free to subscribe and come back for the next one. Not because anyone needs another subscriber count, but because the next decade of computing is shaping up to be one of the most fascinating periods in technology history, and it's genuinely interesting to watch it unfold with people who are just as curious about it as I am. Thanks for watching, and I'll see you.